Hello, this is Dylan Moore, and this is Lab 3 for CPSC 4550. And so basically we got part 1 right here of the lab. I've already run my trace, so I've already got that pulled up from when I ran it. We'll go ahead and go right back up to the top. I'm going to start up here at 1. It says to select the first ICMP echo request message sent by your computer, expand the Internet Protocol part of the packet in the packet details window, and what is the IP address of your computer. So when I go here, it shows me this is my first echo packet, and this says it's a reply. And basically you can see a couple different places. It shows the source here, which is 150.182.130.11, and then you can also find the source address down here, which is your computer's IP address. It's 150.182.130.11. Same as it is here, but this is where you can find it under the Internet Protocol header. And so now we're going to move on to the next one. It says within the IP packet header, what is the value in the upper layer protocol field? So the value we've got here in the protocol field is ICMP1. So that's telling you the protocol that we're using, and the 1 is the digit that it's assigned. And then we go on to the next one, and it says how many bytes are in the IP header, how many bytes are in the payload of the IP datagram. Explain how you determine the number of payload bytes. So if you look, you can look at the total length here and see that you've got your total length, and then you've got your header length, which is 20 bytes. And then if you look down here, data, this is 28 bytes. So our payload is 28 bytes and our header is 20 bytes. For it's -2, so it's a 56 total length of the datagram in bytes. So this has the IP datagram been fragmented? Explain how you determine that. And if you want to determine that, you can look right here, and this is going to tell you fragment offset is 0. So when it says fragment offset 0, that essentially means that there is no fragments to this. If there was a fragment to this, it would give you the byte number where the next fragment's going to pick up at. So like say we did a packet that was 126 with a packet size of 56 set. It would pick up on number 56. And so now we're going to go on to the next one. We're going to go on to the next one. And this one is, which fields in the IP datagram always change form one datagram to the next from this series of ICMP messages? And what we're first supposed to do is we are supposed to click on it by source and then do it again. So now we've got them arranged by source. We've already got our ICMP filter up here. We've had that up there since the start. And yeah, so we've got that up. We got that up there. We've got our sources filtered in. We're going to select the first ICMP echo request message sent by our computer. So we've got our request wise. Looks like sorry about that. My cat's messing around. But I've got it sorted by source. And these are all messages from our destination telling you that the time to live is exceeded on that one, and this is our echoes. So we're supposed to go to the first echo request. And I'm actually going to sort it by number, because that is going to tell me more so about that. So we've got our first request right here at 0.030694 seconds after the start of the scan. And now we can start answering our questions. Which fields in the IP datagram always change from one datagram to the next within the series of ICMP messages sent to your computer? And if we look at the echoes, we can look at the other ones too. But as we go down through, you can see in the data fields, you can kind of see the things that change over there. And you can see that the source address, the destination address, they all change. Each one you go to, because as you're sending one message to someone, they reply from the other one, so they are the source address for that packet, and you are the destination address. So those are going to change. Your checksum values are going to change. And I have noticed that some of the checksum values, they do automatically go to 0x000, and also identification sometimes will go, it'll be the same from 0x000 instead of, the unique identification code that you get. And from what I understand, that is from the router. That's a choice that the router makes, whether it didn't handle the packet appropriately or whether it was programmed to just kind of group it into there, and that was its default selection for either identification or checksum, because the packet wasn't interpreted, or it was just programmed to put that certain type of packet into that form. So if you look, the fields that must stay constant are, the version, that's going to stay the same. The header length is going to be the same. The total length will change. Identification will change, because the identification and the length of the packet sizes change. The identification, that's its own personal ID number. Each one starts with 0x, but the last 4 digits are definitely something different. The flags don't really change too much. It might change from, like, say, this top data packet here. That will change, because you got your fragment offset still at 0, but it says flagged for 0x2 and says don't fragment. But as you go down, it will not have the same flags. And the checksums are going to differ. The protocol is going to stay the same, and the time to live is going to change each time. So TTL is going to change from packet to packet, because each one's different. Each one's been through a different amount of routers, so they've used up a certain amount of their TTL. The protocol is going to be the same, because it's going to be the same protocol we use in this messaging system. And then the checksum is going to be different, because for each packet they're all different, so the checksum is going to be different. And again, source address, destination address, those are going to change each time you change packets, most of the time. And let's see, what's our next one? Describe the pattern you see in the values and identification field of the IP datagram. The differences I see, I think I've already talked about it. You can for sure see that the 0x is always there. Sometimes you do get a 0x000, and we've already talked about that too. But this is 4 different digits, and it seems to be that the echoes, at least, if you look from this one, you've got 0x11AE, and if you go down, you've got 0x11AF. So they are increasing in order. And if we go down to the next one, 11B0. So after F, it resets to 0. After A, it goes to B. And the reset forces B to go up, but 11 stays the same. So it is increasing as it goes for each different little packet there, if they're connected in any way. And so let's see. So we're looking at time to live exceeded. the value in the identification field and the TTL field. This is our first hop. Right here. And so we've got our identification, same thing, at 0x, and then random 4 digits for its own personal identification. And then you've got the TTL field, which is time to live, which is at 63. So it could hit 63 more routers before it is, or I guess it's expired before its TTL has gone. It says, do these values remain unchanged for all IC, MP, TTL exceed the reply sent to your computer? And if you look, we're going to go ahead and just look right here, identification and TTL. And identification, right now we've got it at 0x6978. We go down and you get 0x0000. If you go down even further, you get 0x8226. So yeah, the identification is going to change in the time to live exceeded messages. And if we check on the time to live, we've got 63 here, 252 there, 60 there. So they all change as well. So all of those things change. And again, the reason why is because each packet has a different identification, and the time to live is going to change for each packet as well. Depends on the setting and how many routers it had to go through to get to where it was going. Fragmentation. This is the kind of second part of part 1. It says find the first ICMP echo request message that was sent by your computer after you change the packet size in ping plotter to be 2000. So how I do this is, like we were talking about earlier, you go down to fragment offset, and right now it's at 0. And the whole time that the packet size is set to 56, it's going to be at 0 because the packet's small. It can send that in one packet, no problem. We don't have to worry about it. But when we go up to 2000, we'll find out that it will break it up into different packets. It will fragment the packet. So we're just going to go down until that fragment offset, there we go, it's 1480. So looks like this is where the change occurred. And you can see that by, like I said, the byte offset or the fragment offset changing right there. And this is kind of like you can see there, see 1480. And this is our first one where it goes to where fragment offset goes to 1480. So basically what this is telling you is that it was broken up into at least 2 packets. And the next byte, the next number byte that's supposed to pick up on for the next fragment is going to be 1480. So that means that there are 1479 bytes in this packet, this first packet. And when you go down, and it looks like it's going to skip that, so it's going to consolidate those. But anyways, and also if you look, you can look down here and see under the 2 IPv4 fragments, which is listed under destination address, it's going to tell you your fragment counts too. The reassembled IPv4 length is 1980 bytes, so the total packets is going to be 1980 with the one header, that'll be 20. And with multiple headers for multiple packets, that's going to be 40, but we won't count that. And it also tells you right here, frame 586 and frame 587, those are your fragmented packets. Frame 586 is carrying the brunt of the load at 1480 bytes, and then 587 is carrying 500 bytes. So that's where you get your totals on that. And this is also how you can kind of tell which frame is the first packet, which frame's the second packet. It kind of tells you all of the things. I feel like they've probably updated this program a little bit from whenever this lab was made. So a little bit of it's a little different, I feel like. And now next it's going to tell us to go down to where we changed it to 3500 bytes for our packet size. And so again, we're going to go down and we're going to watch our fragment offset. We're seeing 1480 right now. And if we keep going, we will eventually see a change again, and that'll be where we fit 3500 in packet size. This is going down quite a ways. 1480 There we go, 2960. So here we go. We've hit 2960, and this is where the change occurs. And you can see that right there, clear as day. So we go down to, we've got our fragment offset at 2960. So that basically means that one packet can carry at least 2960 bytes. Now we have the packet size set to 3500, so it is going to break it up. And it looks like we got 3 packets for this, or 3 fragments of this packet, frame 1777, 1778, and 1779. It looks like the first 2 packets, they're going to be carrying the same amount of payload, which is 1480 bytes. And then the last one is going to be at 520 to wrap it all up and finish it off. So there you have your first packet and your last packet. And it says, what fields change in IP header among the fragments? So if we're looking, and it won't let me see these other packets here. So we're just going to move on. And so this will conclude video 1 of part 1.